So today we're going to figure out how an inductor behaves in a circuit. And the circuit we're going to start to analyze is the same circuit we had before, except where we used to have a capacitor, I've swapped in an inductor. Let's remember what an inductor is. An inductor is a coil of wire, which can have a magnetic flux through it. And so what's the symbol for an inductor in a circuit diagram? Well, it's a cartoon representation of a coil of wire. This is the symbol for an inductor in a circuit diagram. And the problem that we're going to solve next video, which I'm going to set up in this video, is completely analogous to what we did with the capacitor. Remember what we did with the capacitor? We had a capacitor here. We started with the capacitor empty, no charge in it. And then we closed the switch and we asked what happened. So here we're going to start with the inductor empty. What does empty mean for an inductor? It means there's no magnetic flux through the coil. There's no current flowing through the inductor. And so no magnetic field energy stored in the inductor. The capacitor stored energy in an electric field. And for an inductor, when there's a current flowing through it, there's a magnetic flux through it, it's storing energy, but it's storing energy in a magnetic field. But what we're going to do is start in a situation where there's no current, no energy stored in it, and then we're going to close the switch and ask what happens. So let's remember what an inductor is and where the physics comes in. The physics comes in from Faraday's law. And in particular, the essence of an inductor is that if the current through the coil is changing, Faraday's law tells us that there will be an electromotive force between points A and B, an EMF. And so what that means is that we now, when we introduce inductors in our circuit, we need to modify Kirchhoff's second law. Kirchhoff's second law we're used to thinking about as walking our finger around the circuit and doing the bookkeeping of electrostatic potential. How does the potential change as you pass the battery? How does the potential change as you pass the resistor? And in the previous case, how did it change when you passed the capacitor? Now we generalize this slightly, so we're not only talking about electrostatic potential, we include in this bookkeeping as we walk around the circuit the fact that because of a changing magnetic field in the inductor and Faraday's law, there is an electromotive force due to changing magnetic fields that creating an electromagnetic force between points A and B. So as we walk around a circuit now, when we pass a battery, the potential is going to change by epsilon. When we pass a resistor, it's going to change by IR. If we don't have a capacitor in this circuit, but if we had a capacitor in it and we walk past the capacitor, the potential would change by Q over C. When we walk past this inductor as we're analyzing this circuit, what should go in that equation will be d phi dt. Okay. The change in the magnetic flux in the inductor. If the current is steady, the magnetic flux is constant, unchanging, no electromotive force. But if the current is changing, the flux is changing, there's a d phi dt. That's what should go in that equation. So before I do the exercise of walking through this circuit and turning the circuit into a differential equation, let me just be careful about signs, and I'll do that over here. So suppose I have an inductor between points A and points A and B. And let's suppose that there is a current flowing through this inductor, and the current is flowing in this direction. Then, so this is the current direction. And now let's suppose that I'm walking across, as I'm analyzing the circuit with my finger, I'm walking across the inductor in this direction. So let's say that I'm circulating in the direction of the current. So I'm analyzing a circuit in which this inductor lives, and I'm walking my finger, my finger is circulating from A to B in the direction of the current. In that case, this contributes an epsilon, which is what? Well, Faraday's law tells us that it is going to be minus L di by dt. It's proportional to di dt, and the proportionality constant is the inductance of this inductor. Now, when we analyze this circuit, we're going to be making an assumption, and it's a standard assumption that's always made, and that is we're going to assume that the only inductance that matters is the inductance of this inductor that you went to Radio Shack and bought and plugged into the circuit in this location. Now, if you were perverse and you took these wires and you coiled them up yourself, when you were laying out the circuit on your circuit board, you like made these wires go in some sort of a swirly pattern. There might be some extra inductance over here because you swirled the wires around. I'm assuming that when I analyze this, that you're not being perverse, and that any small inductance from the rest of the wires I can neglect, that the by far dominant source of inductance in this circuit comes from the circuit element that you bought at Radio Shack, which is the coil that you inserted here. So the only inductance we're going to include in our analysis is the inductance L coming from this circuit element. And in that case, if I walk across this inductor in the direction of the current, the contribution to the differential equation that I get is a minus L di by dt. If instead if I walk in the other direction, so if I circulate this way, and I'm still going to keep the current going in the same direction as I had it before. So if the current goes this way, but I'm now, for whatever reason, as I'm analyzing this circuit, I'm walking across this circuit element against the current. So if I circulate against the current, then this contributes to the differential equation that we're going to build, a contribution which is plus L di by dt. So just as you need to keep track with a resistor, when you walk past a resistor in the direction of the current, the voltage drops, you get a minus IR. If you go against the direction of the current, the voltage rises, you get a plus IR. Similarly, with an inductor, you have to keep track of the sign in the way that I just described, and in fact, it was the same for the capacitor too. Okay, so for this video, what we're going to do is we're going to set up this problem. So with all of the prelude now in hand, I'm actually going to analyze this circuit, and we'll then work on solving the differential equation in the next video. So to set this up, I have to pick a direction for the current. I'm going to notice that the battery has the positive terminal here and the negative terminal there, and motivated by that, I'm going to choose my direction of the current like this. But notice that that's an arbitrary choice. In fact, I could choose my direction of current the other way, go through the whole exercise, this video and the next, and I would find a solution that would have a minus sign relative to what we're going to get by choosing the current going this way. So you can't actually go wrong here. If you had picked your current going the other way, do your full analysis. Your answer will be minus of my answer, and in fact, we will agree because I defined my current this way and you defined your current the other way. Okay, with the direction of the current defined, I can now walk my way through the circuit. So I'll start here. I'm walking through the circuit, and I'm going to choose to walk my way around the circuit in the same direction as the current. I start here, I walk. I'm crossing the battery, and I'm going from the negative terminal to the plus terminal, so that gives me an epsilon. Continue walking my finger, and I get to the resistor. I cross the resistor, and I'm crossing the resistor in the direction of the current, so that means I'm going from high potential to low, so I get a minus IR. Continue walking, and I get to here. I'm going through an inductor, and I'm walking through the inductor in the direction of the current. I remember my sign. That gives me a minus L di by dt. Keep walking. the switch had better be closed. So I'm imagining I'm describing the circuit just after closing the switch. Switch is closed, keep walking, and I'm back to where I started. Back to where I started means this collection of terms has to add up to 0. So this is my differential equation. I can rewrite it as a differential equation for di dt. And that will be 1 over L times epsilon minus IR. And this is where we're going to stop today. So I've formulated the problem. I have closed the switch. And I have obtained the differential equation that's going to describe what happens. We're going to solve this differential equation in the next video. But before we stop for today, let me just take a little bit of a further look ahead. First of all, let's notice that actually you know how to solve this equation, because this is actually the same differential equation that we solved for the capacitor. What's the difference? Well, the difference is that for the capacitor, the terms that came in, there was a term that had a Q in it, and there's a term that had a dq dt. Now there's a term that has an I in it, and there's a term that has a di dt. And so from the math point of view, it's the same equation. And so when we solve this equation, we're going to rely on the things that we learned how to do last time. Because from the math point of view, it's the same differential equation. You just changed a Q to an I. But from a physics point of view, this has an important consequence. This explains why I didn't just go right from the start and put an L and a C and maybe an R also. But I didn't put an L and a C in the same circuit. The reason why, when I wanted to start considering inductors in a circuit, the reason I started with inductors in a circuit that had no capacitor is that resulted in me getting a first order differential equation. Whereas let's think what would happen. Suppose that I had a C somewhere in the circuit. Then I'd have a term in this equation with a Q in it. I'd have a term with an I in it coming from the resistor. And I'd have a term with a di dt coming from the capacitor. But I is dq dt. So di dt is d squared q dt squared. So I now have an equation with a q in it and a d squared q by dt squared. So you can already see that as soon as we put L's and C's together, we will have a second order differential equation, not a first order differential equation. And that's why I haven't done that quite yet. So in the next couple of videos, we're going to analyze this problem, and then we will bring capacitors back in, and all of a sudden we'll have a second order differential equation. But looking ahead to that moment, it will turn out that the second order differential equation that we get is the simplest possible second order differential equation, and it's one you all know how to solve because it's the one which in 801 described a simple harmonic oscillator. And we'll get to that a little bit further down the road. And that's it for now.